This was a presentation given on September 27th at a GMP Forum meeting regarding some new methods to investigate the dissolution of API and controlled release formulations. These new methods were applied to reverse enteric coating formulations. A reverse enteric coating is a polymer coating which inhibits the dissolution of the underlying material in pH conditions of the mouth, but still allows very rapid dissolution at pHs of the gut. The specifics of the formulation studied here were microspheres for an oral solution. Microspheres consist of a core with an enteric coating, which is an acrylate polymer. The microsphere is approximately 200 microns in diameter. Below is a snapshot of the dissolution of the microsphere and coated microspheres at different pHs. At a pH of 5.5, the uncoated microsphere dissolves over approximately 15 minutes. At 4.5, there's very rapid dissolution. At a pH of 6.8, the mouth conditions, the polymer keeps the underlying formulation from dissolving very rapidly. And at 5.5 is an intermediate. The following is a time-lapse video of approximately 15 minutes condensed down into 30 seconds. Again, at 4.5, or stomach conditions, the polymer dissolves rapidly, releasing the underlying core. We can see in that same time frame, the core does undergo substantial dissolution. You can see apparently some of the API coming out through cracks. Conversely, at 6.8, the mouth conditions, the polymer keeps the core intact and we do not see much dissolution. And at the intermediate pH of 5.5, there's substantial swelling of the polymer, subsequently followed by dissolution before it swells as much as we'll see from some other polymer types. The goal of this project was to develop some techniques that could screen the polymers without having to go through the process of creating the microspheres, therefore minimizing time and the amount of material. A technique used quite often in the electronics industry is called a Quartz crystal microbalance, or QCM, and is used to study the dissolution rate of photoresist polymers. A quartz crystal microbalance is based on a piezoelectric material. A piezoelectric material is a material with quantum properties such that an electric field can cause deformation of the material. Therefore, an alternating electric field can cause a periodic oscillation. In this case, for an AT-cut quartz, the crystal deforms along its plane in a shear motion. By putting a material on top of the crystal, it changes the resonant frequency of the oscillation. The resonant frequency of the oscillation is related to the mass through some constants, physical parameters of the crystal itself. We use a lock-in amplifier to measure the resonant frequency, therefore knowing the change in mass over the time of the experiment. The experiment begins by spin coating a polymer on top of the crystal and then flowing a buffer solution of interest over top. The initial flow causes swelling of the polymer and a decrease in frequency of the oscillation. As time continues, the polymer begins to dissolve and the oscillation frequency increases. Again, by measuring this frequency change, we know the change in mass on top of the crystal and therefore can estimate the dissolution rate of the polymer. Here's an example comparison between QCM measurements and dissolution. On the left is mass versus time for a QCM measurement at varying pHs, and on the right is mass versus time for a traditional dissolution measurement. If we look at the QCM measurement, at a pH of 4.5, we see the polymer film swells and then rapidly dissolves within under a minute. Conversely, at a pH of 6.2, there is some minor swelling, but no apparent dissolution. And finally, at the intermediate pH of 5.5, there's swelling followed by dissolution of the polymer. This correlates with the traditional dissolution measurement, where we see at a pH of 4 or 5 there's a very rapid release of the API, at a pH of 6.2 a very slow release of the API, and at 5.5 an intermediate release of the API. So again, the two correlate very well. However, the QCM measurement is seen to be done in approximately tens of minutes, whereas it takes several hours to do a traditional dissolution, and that's because of the amount of mass. The QCM measurement uses approximately a few tenths of a milligram of polymer. It also requires no PI, therefore avoiding the complication of having to prepare microspheres. QCM also provides some information about the coating stiffness. For a stiff coating, the coating oscillates in phase with the crystal, and very little energy is dissipated. As the polymer is plasticized, the film softens and oscillates out of phase with the crystal, jello-like, and dissipates energy on each oscillation. The instrument measures the amount of energy required to oscillate the crystal at the same amplitude and frequency. Thus we get some information almost rheological, such as the shear modulus of the film. Here are two plots comparing the mass versus time and the resistance versus time. Again, at 4.5 there's very fast dissolution, and at 6.2 very slow. The resistance shows very similar effect. At a pH of 4 or 5, the resistance goes up very quickly as the polymer swells, but then immediately drops within under a minute, approximately 30 seconds, as the film dissolves and the energy dissipation decreases rapidly. At a pH of 6.2, the polymer film stays fairly rigid and never requires much energy. At a pH of 5.5, the swelling causes it to become very squishy or jello-like, dissipating quite a bit of energy, and then as it dissolves, the amount of energy required decreases. QCM can also be used to measure the effects of coating thickness. Here we see mass versus time, or different amounts of mass on a crystal. 1x, 2x, 4x correspond to the number of times of spin coating on the crystal. As expected, as the mass of the polymer on the crystal increases, we dissolve more mass during the dissolution run. However, the peaks stay roughly at the same time, which makes some intuitive sense since the polymer and the buffer solution are the same. If we look at the resistance, we do see a slight shift to lower times for the 1x spun crystal, for the lower mass. It turns out this is due to a drying effect. When we only put one coat on there, there is minimal time between the coating and the subsequent dissolution, whereas when we spin coat multiple times, each spin coat gives the crystal, the underlying layers, more time to dry. We can study this more accurately using the QCM. Again, mass versus time, this time for films dried for different amounts of time. 30 seconds, 5 minutes, 1 hour, and 2 days. The plot clearly shows that as the film is dried for a longer period of time, it takes longer for the polymer film to dissolve at the same conditions. The resistance curve shows very similar effect. Very interestingly, we can collapse these curves down almost overlapping them onto a master curve. Here we have mass versus time. Again, from the same plot that we had on the last graph, on the last slide, of 30 seconds, 5 minutes, 1 hour, 2 days. If instead of plotting mass versus time, mass is plotted against the logarithm of time, the curves become very similar in shape and are offset from each other depending on the amount of drying time. If we pick a point on each one of the curves, say the maximum, and plot that maximum versus the drying time, we can fit a curve through that, in this case a line. This relates the drying time to how much they are offset from each other, or a scaling factor. We can then use that scaling factor to scale our curves, and they collapse nicely almost onto a master curve. This conveniently allows us to predict the dissolution rate for other drying times. For instance, if we were to inspect what would happen at 2 hours, we would take our master curve, we would look at 2 hours, and we would find what the scaling is, and then we would apply the inverse of that scaling to get back what the dissolution time would be at 2 hours of drying. QCM also affords us the ability to change the dissolution conditions while the experiment is being run, slightly easier than a traditional dissolution measurement. Here we have mass versus time. This time we're going to have step changes in the pH. 5 minutes at a pH of 6.8, then another approximately 5 minutes at a pH of 6.2, followed by a step change to a pH of 4.5. And this is done for polymer films dried at 10 minutes, 30 minutes, 45 minutes, and 12 hours. Looking at the 10-minute data, we see that at a pH of 6.8, there is some swelling of the polymer at the pH of 6.8. When a step change to 6.2 occurs, there is more rapid swelling, followed by a fairly quick decrease in mass as it starts to dissolve. And then at a pH of 4.5, there's even a faster decrease in the rest of the dissolution of the polymer. This is similar for the 30 minutes and 45 minutes. However, if the film is dried for 12 hours, there is minimal swelling for a pH of 6.8 or 6.2. However, when the pH is shifted, step change to 4.5, there's still the very rapid swelling and release as needed. Again, the resistance shows very similar information here. QCM therefore provides a relatively quick way to screen the dissolution rate of polymers under different conditions and using different properties of the polymer or different components to put in with the polymer, such as plasticizers or surfactants. However, it provides no information on the actual visual of how the polymer dissolves. We can use another technique to get some visual information, specifically optical coherence tomography, OCT. OCT is an interferometric technique based on low coherence. We're essentially using a broader bandwidth of radiation. The axial resolution is determined by that bandwidth. It has an acquisition time on the order of tens of seconds for a 10 by 10 by 1 millimeter sampling. And the penetration depth depends on the amount of scattering in the sample. To the right, it shows a schematic of an OCT. This is mostly just a Michelson interferometer. We have the radiation coming down, goes through a beam splitter, it hits a reference mirror, which moves back and forth. The other part of the radiation goes to the sample. They are recombined at the beam splitter and go back into a camera. An example use of an OCT is shown here for an osmotic release tablet. Here we see the main tablet. There is a film on top of the tablet that refracts the light back, and we can see the laser drilling. And again, we can scan in both lateral directions and obtain the information from the axial, from the interferometry, and get a three-dimensional image shown here. An example use of the OCT for the current project of the reverse enteric films is shown here. On the top is a film cast on a microscope slide, and it's going to be dissolved at a pH of 4.5. The plot on the image on the left is at the beginning, the first cast film, and on the right it's near the end, not the exact end where the film would be gone, but near the end. On the bottom is a film of the same polymer cast on a microscope slide but dissolved at a pH of 6.8. On the left is again the start, and on the right it's near the end. Just from the static images we can kind of see that for a pH of 4.5 it looks like the film just gets dissolved from top down, whereas at a pH of 6.8 we see that it looks like there's quite a bit of swelling. It goes from almost probably a 50% increase in the thickness. The following will show a time-lapse video of these images. Again, at 4.5 we see that the polymer dissolves almost from the surface downward. and relatively quickly. This experiment at 4.5 was probably on the order of about an hour. At a pH of 6.8, the film undergoes tremendous swelling before it finally dissolves. It looks like this experiment was cut a little soon. There's still some residual polymer that's apparent there. But it did swell before it was able to dissolve from the microscope slide surface. It's worthwhile to use these techniques to explore a new polymer that has slightly different characteristics. First, looking at the QCM measurements. Again, mass versus time. We'll call this for a polymer B. It behaves very similar qualitatively to the first polymer. At a high pH, there's very little dissolution. At the lowest pH, there's rapid dissolution, and at an intermediate pH, there's intermediate dissolution. The pHs are shifted slightly from the first polymer due to its chemical composition, but again, the qualitative trends are the same. The one interesting difference between this and the previous polymer is the magnitude of the swelling. The first polymer swelled on the order of its mass, which is on tenths of a milligram, whereas these experiments suggest that there is swelling on the orders of hundreds of milligrams. Also, the dissolution is very sharp compared to the more gradual dissolution seen with the other polymer. It'd be interesting to try to understand why these two polymers behave differently. For that, we can use the OCT instrument again. On top is the first polymer we'll study. We'll call that Polymer A. On the left is the start of the experiment. At the end is near the, on the right is near the end of dissolution. On the bottom is the new polymer under study, Polymer B. Again, the left is the start of the dissolution. On the right is near the end. We immediately can see the difference between the two polymers near the end of dissolution. For Polymer A, it swells uniformly. For Polymer B, it looks like it actually begins to delaminate. So let's observe what happens dynamically over the time of this dissolution. The top again shows what we've seen before. Polymer A starts with just a regular film and begins to swell. It swells probably by about 50%, and it'll slowly dissolve. Polymer B, on the other hand, swells for considerably longer time and a larger amount, almost doubling its size. Then a very interesting thing occurs before the experiment is done. The polymer actually delaminates from the microscope slide. It turns out that Polymer B is relatively insoluble in the buffer solution, whereas Polymer A is soluble. So therefore Polymer A swells and then finally dissolves, whereas Polymer B swells but doesn't dissolve. The OCT measurements are not done under flow due to some of the problems with reflection of the surface with ripples. Therefore the QCM does show slightly different, where the flow probably causes the undissolved polymer to eventually just rip from the crystal surface and float away. We can compare these two polymers again right with the formulation itself. On the top, Polymer A, again we have the core, and then the three pHs, 4.5, 5.5, 6.8. And below, Polymer B, same pHs. And what we'll see is that we're at 4.5, both of them are fairly soluble, same with 5.5. The most interesting thing probably comes between 5.5 of Polymer A, where it's between its two extremes of rapid dissolution and no dissolution. And for Polymer B, that difference occurs more at around 6.8, where there's not rapid dissolution, but there is some during the course of the experiment. Remember that Polymer B is much less soluble, and therefore it will probably undergo much more swelling. So again, comparing the 5.5 of Polymer A to the 6.8 of Polymer B, we see that for Polymer A it swells and then dissolves. For Polymer B, it swells considerably more, and because of its insoluble nature, we don't really see the polymer dissipate as we do with Polymer A. This suggests that all three experiments do correlate well with each other. What's actually occurring most likely with the QCM is we get the very swelling that we've seen with OCT, and then it delaminates and just floats off, and therefore a very abrupt change in the frequency. And the 800 milligram suggestion of the swelling is probably not that far off, given the fact that it probably delaminates from several spots on the crystal, trapping water underneath. We can study to some extent the dissolution of the API underneath the polymer film using some techniques. Since we know that the polymer film swells considerably with water, we expect that there might be some dissolution of the underlying API before the polymer is completely dissolved. One technique to try with this would be using polarized light microscopy. In this setup, we cast the core material on a microscope slide, then we spin coat a polymer layer, and we view the dissolution of the measurement under polarized light. The image down in the bottom left is a polarized light microscopy image at the start of the experiment. Since the API is birefringent, the only bright spots that we should see are where we have an optically active material, such as the API. When the API dissolves, it is no longer active, optically active, and therefore the image goes completely black. To quantify this over the experiment, we can plot the total intensity that we see from the microscopy as a function of time. Here we see the beginning of this experiment. The water is penetrating through the polymer. At some point, it dissolves the polymer, and we start to see the API float about. If we look at the intensity on the right, we see the intensity decrease right from the beginning, and there's a bit of a knee where we've seen from the image that it was very likely that the polymer dissolved, allowing the API to float about. Now, it is a very difficult measurement because as the polymer dissolves, it changes the refractive index in the focal plane, and the microscope has to be readjusted periodically for focus, and hence some of the periodic changes out of focus during the experiment. Another problem with the experiment is it only works for birefringent materials, which is fine for most APIs since they are optically active. However, it doesn't tell us anything about the excipients, such as the polymer or the binder in the core. A very similar measurement that we can do, but get more of this chemical information, we will use spectroscopy. Specifically, we will use Attenuated Total Reflectance, ATR, infrared spectroscopy. In this measurement technique, there is a crystal in which the IR radiation is passed through. It is totally internally reflected, and each reflection point produces an evanescent wave that penetrates above the crystal surface, in this case into our core and polymer material. The experiment here is called a triple bounce. The radiation is actually bounced 3 times off the crystal surface before being recorded. We begin the experiment. We add water to the top surface. The water penetrates through the polymer into the core. As the experiment proceeds, we should see an increase in the intensity of absorption at the water band, and then a decrease in the absorption of the polymer band, and a decrease in the absorption of anything that's being dissolved in the core material. The bottom left shows the absorption as a function of wavelength, with multiple spectra collected over time. If we look at the spectra, we see that in the wavelength range of water, we see a growing absorption intensity, and thus that is the measuring of the water as it gets close to the crystal surface. At the same time, we see a decrease in the signal of the polymer as it is dissolved and most likely being brought up further out of range from the evanescent waves. And we also see a decrease in the absorption intensity of the API material. This can be quantified and viewed a little bit easier if we plot the absorption at specific slices in our absorption band, in our spectrum bands, as a function of time. You see at the beginning of the experiment there's a lag as the water has to penetrate through the material and get to the crystal surface. After that initial lag, we start to see the water intensity growing in. We see the polymer being dissolved. And for this particular polymer experiment, the experiment used here, we see that there's very little change in the API signal, suggesting that the API is not leaving the vicinity of the evanescent wave. We can compare the two polymers, Polymer A with Polymer B. We have absorption versus time for Polymer A and for Polymer B on the right. Looking on the left, the beginning of the experiment again, there's initial lag as the polymer, as the water penetrates through the layers to get to the crystal surface. Then we see the water intensity growing in. We see the polymer being dissolved and its intensity decreasing. And for Polymer A, we see a small but very noticeable decrease in the spectral intensity of the core material, specifically the API, suggesting that we are dissolving the API, and again it is moving through the polymer film up above, well above the polymer film, out of reach of the evanescent wave. Conversely, if we look at Polymer B, we see that after the initial lag there's the increasing of water. However, if we look at the scales, we see that the absorption is approximately an order of magnitude lower than Polymer A. That makes sense since this polymer is a bigger barrier. Also, we see that there's a much slower dissolution rate of the polymer relative to the water compared to Polymer A. Remember that Polymer B is relatively insoluble, so we don't expect that to go away as easily. And finally, we note that the core, the API, is not dissolving, suggesting that the insolubility of the polymer is trapping the API beneath the surface, keeping it in contact with that evanescent wave. The work in progress is we would like to see if we can quantify the information that we're gathering from the QCM, OCT, and the ATR measurements. To do that, we will need accurate dissolution data from the spheres. One method is to put a sphere on top of the Quartz Microbalance and measure a single sphere dissolution. Unfortunately, the mass of a single sphere is on tens of nanograms, and the resolution of the QCM is the order of nanograms, and therefore we really don't have the resolution for a single sphere. We could use multiple spheres, as shown by this OCT measurement of the crystal. However, during the measurement, a loss of a sphere makes it ambiguous whether we are losing mass of the polymer film or the core, or if the sphere is dissolved. Therefore, it would be easier if we could do a single sphere. What we really need is an oscillator with a lower stiffness and therefore the sensitivity needed for the single sphere. Fortunately, it turns out that we already have that in-house. The cantilevers used on atomic force microscopy have approximately the right stiffness to be able to measure the mass change of a single microsphere. On the left, we see it's based on the same principle. As the mass of the microsphere decreases, the oscillation frequency of the cantilever increases. On the right, we see an actual photograph image of a microsphere mounted to a cantilever. The problem currently is keeping the microsphere attached to the cantilever during the entire measurement. It is interesting that the sensitivity estimated for the cantilever technique will be on the order of picograms, and some papers report femtograms, therefore giving several orders of magnitude increase in sensitivity over the QCM. So in conclusion, some of the benefits of the QCM are very simple sample preparation. We can simply spin coat the polymer. It's a fast measurement, tens of minutes, and it's inexpensive. The instrument costs approximately $5,000, and a single crystal on the order of $10. So multiple crystals can be purchased, and DOEs run on them at the same time. The drawback is it can be difficult to understand some of the dissolution information without visual confirmation of what is happening. Fortunately, combining the QCM with the OCT provides that extra visual information. Again, the sample preparation is fairly simple, spin coating on a microscope slide. The measurement time is a little bit longer, hours, because the film is a bit thicker than we'd use for a QCM based on just the resolution that we can get with the OCT. The cost is a bit more. It's about $40,000. It's also very material sparing. It does not use API if we don't want to. And for the requirement of the polymer film itself, it has to be relatively low scattering. So These enteric, reverse enteric type coatings are fine. However, things with iron oxide or titanium dioxide probably are not as viable given the high scattering. And finally, if we want to try to understand the multiple components dissolving, we can use some spectroscopic techniques, this attenuated total reflectance. Again, the sample preparation is quite easy due to the geometry of the setup. We can't spin coat, but we can use evaporative drying. The measurement time is a bit longer again because the film thickness is a bit bigger, but it is overall material sparing compared to a traditional dissolution measurement, and the instrument is a bit more expensive.